and inspiration is actually, you know this guy Feynman? Do you guys know this guy Feynman?
Yes, sir.
Who was he? How many of you have read his lectures? I just want to know in 10 plus 2. Have you read his lectures?
No.
So there are very famous lectures by Feynman. It's called Feynman's Lectures in Physics. In our 10 plus 2, we used to look at it. We were not able to understand everything. But I remember in my 10 plus 2, I used to look forward for Feynman's Lectures in Physics. There is also a very nice book where he wrote about his kind of experiences. And that's called Surely You Are Joking, Mr. Feynman. Okay, so that's an interesting book. And nowadays it's YouTube. हमारे ज़माने में नहीं था, but nowadays it's YouTube, so you can listen to some of his real lectures on YouTube. And one of the famous lectures are called There Is Plenty of Room at the Bottom. In 1960, Feynman gave this lecture. If you see him in Berkeley, or maybe Caltech, I don't remember. I think it's Caltech. Rajan is here, so Rajan can correct me if Feynman lecture if I'm making a mistake here. Okay, he said he's wearing like shorts. Okay, a professor in 1960 going to the classroom and he's not wearing full pants, it's shorts. Okay, and he's giving a lecture, 1 hour lecture. You should listen to lecture Feynman on YouTube archive videos. There are many videos on him and learn about it. In 1960, he said that there is plenty of room at the bottom. How am I going to make these materials? How I'm going to engineer new materials which can solve this problem? Just like Haber was able to think, he was able to make this catalyst, but he didn't think how it is functioning. But at the molecular level, you have these active sites which can trap a molecule and fix it. Okay, all of this Haber can design it. Okay, same way Feynman, the Richard Feynman was telling that you can do many things at the bottom, and that's called nanotechnology. He said, you see all of these different colors, you can see that there's red, there is green, there is, do you think what kind of material is that? How many materials are there in this bottles? Anybody can respond? Can anybody respond? How many types of materials are there? Anybody? 1, 2, 3, 4, 5, 6, 7, 8. 8 bottles, all different colors. Do you think how many types of materials are there in this? Astha, you were saying something? Just make a guess.
So just one?
Just one. Who said that?
So Lakshya.
Lakshya. So you tell me, why do you think they're just one, not 8 materials? Why they are showing different colors?
Because these are ionized particles or something like that?
Not ionized. It's the same material, same oxidation state, everything is same. These are cadmium sulfide particles, nanoparticles, and they are all showing different colors. Why do you think they are showing different colors?
Because different lights are being shined at them.
No, it's the same light. It's the same light. These are quantum dots. These are small nanoparticles. Why they are showing different colors? Great.
So different wavelengths.
It's called different particle sizes. Okay, so one size may be 4 nanometer, the other is 5 nanometer, the other is 6 nanometer, 7 nanometer, 8 nanometer, 9 nanometer, and they all show different colors. Okay, can anybody explain why?
So they reflect different wavelengths of light because of different size.
I agree with you, because there are different, but why? Why different nanometers there? Like for example, this is iron. Let's suppose this my glass is iron. I make small pieces. I make 1 meter, 2 meter, 5 meter, 10 meter. Are they going to change the color? No, they are all going to be same iron, ferromagnetic, no changes. Here, if I'm reducing the size by 1 nanometer, 5 nanometer to 4 nanometer to 6 nanometer, I see different effects. Okay, different ferromagnetism. Then it becomes iron is behaving like gold. Gold is behaving like iron. One is paramagnetic, So all these properties are changing by each nanometer scale. Why is that happening? Anybody can respond? Oh, wow, awesome. You are PhD student or under 10+2? Yanshu, you are a PhD student? 10+2, great man, you are awesome. Homo, lumo, everything you are explaining. But why it doesn't happen when I'm doing it with the iron bigger sizes? Why it doesn't happen? So you are. So let's suppose I take, instead of nanoparticles, I do it with micrometers. 1 micrometer, 2 micrometer, 3 micrometer. Do I see the same effect or not? With iron changing to gold, gold changing to silver, does it happen? Like iron changing completely its properties to look like gold, or gold changing its properties to look like iron. If ferromagnetism changes to paramagnetism, something like that. Does it happen at micrometer? Yeah. So it's not radio wave, it's nanometer, 10 power minus 9. That's why we call nanotechnology. Why we call nanotechnology? Because these things happen only at nanometer level, 10 power minus 9. It doesn't happen at the length scale of 10 power minus 8, 10 power minus 7, 10 power minus 6, 10 power minus 5. Only at that, when you hit 1 nanometer, 2 nanometer, 3 nanometer, the properties starts changing. The material starts behaving like you have a big iron. You make pieces. 10 power minus 6 micrometer iron will be the same as 1 meter iron. Okay, big block of iron and a small particle which you can't even see, a micrometer of iron, will be the same. But as soon as you make a nanometer of iron, the properties starts changing. Why it is changing? What is happening? Anybody can respond?
Sir, is it due to diffraction through the particles?
Yes.
Different wavelengths diffract through different sizes.
So you are coming close. You probably don't know the exact answer. The reason is that till 10+2 you are only taught Newtonian classical mechanics. Do you know? F is equal to ma. Okay, you are taught about this. Okay, Newton's law of motion. This physics is governing all the physical phenomena in the bulk scale. So materials properties are governed by Newtonian mechanics all over the scales which we are observing. Iron is ferromagnetic. It will be ferromagnetic if you make small pieces, very small pieces, it's still. But as soon as you reach 10 power minus 9 or the nanometer scale, the physics changes. What physics now governs? Is it Newtonian or something else? Do you have an answer?
Quantum?
Wow, wow, this is Manan girl. Manan, have you read anything about quantum? What is quantum?
Sir, I've read some bits of it, some observations. I know about the Stefan Gerlach experiment,
Yes.
and that's it actually.
Action and all, because of the atomic spacing is actually governed more and more by quantum mechanics. Okay, and that has a different physics, completely different laws. Okay, quantum mechanics now starts ruling the properties of the material. So if you are changing now the length scale, in Newtonian, if you are making small pieces of iron, the physics doesn't change, the properties doesn't change. But as soon as you hit quantum confinement, quantum enigma starts building up, and you will start seeing that the properties of the material changes as you reduce the particle size by 1 single nanometer. 5 nanometer is a different iron than 6 nanometer. 6 nanometer is different than 7 nanometer particle. 7 nanometer is different than 8. These properties are really exciting. So far, almost all the Newtonian mechanics is saturated, but quantum mechanics and the nanoscale properties are not saturated. This is to explore how you are going to engineer the material at the nanoscale, at the nanometer level, so that you can change the properties. Same catalyst material may be inactive, but if you make changes at the nanoscale, it may become active and give you the product the way you want it. And that's what nature is doing. Enzymes are doing the same way. At the nanoscale, they have these cavities which are doing the job so efficiently, and they may have be quantum confined, with quantum mechanics, governing quantum mechanical bond associations happening at the confinement and gives you the product. Nature has this machinery in design. The same way you will see you have to build your catalyst materials from these simple 2D to 3-dimensional environment to solve this problem, which I'm talking about. Break water, using sunlight, combine it, gives you more energy. So overall cycle, in the entire cycle, you drive more and more energy and in the sustainable manner. That's how you are going to sustain the planet, just like the nature is doing. Solution is right there, that you have to think about quantum mechanics and play around with quantum mechanics, or at the nanoscale, what is called nanotechnology. That's going to solve both problems, energy and climate change. Clean energy. You want to reduce the carbon footprints or remove the carbon footprints, this is the solution. Does it make sense or not make sense? Okay. Now,
So,
everything, yeah.
So when you talk about changing properties of materials, are you talking about arranging the atoms on a nanoscale?
At the nanoscale, because then you are changing the particle size. 6 nanometer particle of iron may have 200 atoms. 5 nanometer may have 150 atoms particle. So these are the different sizes of clusters which have certain numbers of atoms, and that will, each particle will behave differently. That's what all chemists are trying to do for centuries, to turn iron into gold. Now it is possible, because as soon as you are able to change the chemical properties of iron from ferromagnetic to paramagnetic or something like that, you are converting the element from one element form to the other, because the properties are changing. That's what exactly I'm talking about. And then you can have these 3-dimensional cavities which can capture and give you the product the way you want it. Then you can solve the sustainable problem on Earth. And this is how you have to think. In 1960, when Feynman was delivering this lecture in Caltech, people were laughing. You read that lecture, listen to that lecture, and read his book. Surely you are joking, Mr. Feynman. And you will hear that how people were laughing when he was talking about there is plenty of room at the bottom, that you can manipulate the material at the nanoscale, when Feynman was saying it. But today we know that we have high resolution microscope at IIT Delhi. You can come and visit. You can look at the material. You can engineer it atom by atom. Okay, all of this is possible. Atomic force microscopy, transmission electron microscopy. All the tools are there to manipulate the material at the nanoscale. You just need to play around with your hands and the right tool in your hand to engineer the material. That is the promise of the century that you need to look forward for. Okay, that's what you are made for actually. If you are in science, I bet 90% of you will be working at the nanoscale, because that's where the future is. All the Newtonian world is already discovered. So if you are looking for biology, biochemistry, or you're looking for medicine, or you're looking for materials, or you're looking for energy problem, climate change, as I am discussing, solutions are only coming as you manipulate the material at the nanoscale. If you're playing with viruses, all of this DNAs, everything is happening at the molecular level or at the nanoscale, where quantum mechanics is guiding force in establishing different physical relationships. Okay, this is my really thoughtful and profound comment for your future, that which you are looking ahead. Okay, now in catalysis, when we talk about Feynman, I'm from catalysis, and that's very big field: photocatalyst, electrocatalyst. I'm talking about enzyme catalyst, biological catalyst, chemical catalyst. We have been doing this for last 100 years. Haber didn't knew about that catalyst, but that was actually a nanotechnology from 1920. This is George Bush started calling it when you were born in 2001. He's made a center for nanotechnology, so the world became aware of this term nanotechnology. Catalysis people are the forefront in the science, which knew and have been manipulating this material at the nanoscale for a long time. It's only in the last 1998 and 2005, the time when you were born, we started seeing this, that it's actually happening. And that's how the Gerhard Old got the Nobel Prize, and he explained what is happening at the nanoscale. But without knowing, they have been actually doing the real nanotechnology for hundreds of years. And that's a blessing, and that's the promise that you can do more, and you can lead the forefront discoveries in science by doing catalysis. Okay. And catalyst surface is a really amazing surface. It's not the particle size. It has different shapes and different atoms. As you see, there are corner sites, there are terrace sites, there are facets. All of this is different possibilities on the catalyst surface, which enables different types of reactions. And I said, this is just two-dimensional. You can also make three-dimensional cavities. Now you have not just different sizes that you are making 3 nanometer size, 4 nanometer size, 5 nanometer size. Catalysis is much ahead. Now we are able to synthesize different shapes like cube, 2 nanometer cube versus tetrahedron, octahedron, cubo-octahedron, sphere. All of these shapes you can make, and all of them may be of different size, same size, but they show different reactivity. Okay, so all of these engineering tools are now possible, which you may take whenever you take this as a research topic, that you can make, and you can guide a reaction the way you want it, that you want this reactant to make this product with very less energy. Just like I said, water making hydrogen with very less energy. You can dictate all of this at the nanoscale because you have tools to characterize and you can make. Now I'll show you a video which is done by my advisors at Van Sontens at Netherlands, and it will tell you how carbon monoxide combined with hydrogen on a catalyst surface to make fuels, hydrocarbon fuels. That's known as Fischer-Tropsch reaction, and how the catalyst surface at the molecular level is engineered to make large C16 or C15 or C8 diesel and gasoline range fuel from carbon monoxide and hydrogen. And you watch this movie for 2-3 minutes and tell me what kind of work is this? How long does it take to make a movie like this? That's my question after the movie. Okay, so let's watch this movie. Let me know if you're able to hear it. Oh. Are you able to
This
hear
animation shows the fate.
Are you able to hear the audio?
Yes, sir.
This animation shows the fate of carbon atoms on different types of ruthenium nanoparticles. Dihydrogen decomposes rapidly. However, on a dense planar surface, carbon monoxide decomposes slowly into carbon and oxygen. Since there is a low concentration of free carbon atoms, methane and water are the only products. Only on particles that are large enough to support an open corner with coordinatedly unsaturated ruthenium atoms can the formation of hydrocarbons occur. On the highly reactive ruthenium atoms in this open corner, carbon monoxide rapidly decomposes and generates enough free carbon to sustain a chain growth mechanism. To allow this process to continue, it is necessary for newly formed carbon-hydrogen moieties to move away from the dissociation site. This mechanism of rapid carbon monoxide dissociation and carbon relocation was discovered in quantum mechanical calculations.
So I am ending here. I think it's almost time, and there's 5 minutes. I want to give more for questions, but let me finish this. This is I showed you 2-minute movie, which is showing how carbon monoxide, CO, breaks carbon and oxygen. Then C plus C plus C plus C, it makes C6 or C7 like fuels, hydrocarbon fuels, which are used as gasoline or petroleum products. How you increase the chain and stop it right there at the product, which is your petroleum range product. How do you make that catalyst function? So it has the corner sites, as I was showing in the catalyst structure. These atoms arranged in a manner that it gives you the right chain, and you can engineer the catalyst material that way. What do you think? How long does it take to make a movie like this? Anybody can respond? This is like something somebody sends you on your WhatsApp and you watch a 2-minute movie clip. How long does it take to make a movie clip like this? Anybody can respond? Just make a guess. Anybody can respond.
Sir, maybe months.
Years.
Who said that? Kalpana.
Several years.
Several years, Astha. Why several years, Astha?
Because there's so many possibilities for so many shapes of catalysts and such a variety of catalysts. the research of each one of them trial and error method or by estimating would take a lot of time, sir.
So Asta, I must commend you. I have presented this in my IIT first year BTech class. And some people say, oh, maybe 1 month or 3 months, because these are animations, like cartoon animations. Okay. But it takes several years. That is true. Anybody else responding? Anybody else responding? So my whole, Manan, you were saying something, yeah, Manan.
No, sir, it was an accident.
Yeah, so Asta, I must give it to you. You are really awesome. See, in life, nothing is achievable in a short period of time. I'm telling you. You are 10+2. Most of you come to IIT. In the first semester itself, you think, okay, I will have a startup. I don't need to study, and I will become Flipkart owner at IIT Delhi. Not everybody ends up there. The whole thing is you have to study. You have to go deep in a subject to become something like this, to really create something. So you have to accept it that it takes time. It's not. It's like a kachua and tortoise and crocodile. Like what was that? A rabbit. Okay. So you have to be slow and steady. Okay, in your studies. So that's my positive, encouraging point for all of you, because this kind of movie is not created in 1 month of animation. This requires several PhDs. I know Von Sonten, I know Professor Von Sonten, he's now 80-year-old, but he has been doing this work for the last 40 years. So 40 years of understanding is going in how you dictate the catalyst materials or design the catalyst materials to give you the right job. Don't feel discouraged. This is every single move in this movie is calculated. How it is calculated? Can anybody tell me? Every single move, like atom moving like this, how it is calculated, where it is calculated. Anybody?
Spectroscopy.
Not spectroscopy. These computer simulations are performed on a supercomputer, high performance computing clusters, probably one of the best clusters in the world. Where maybe these calculations are done. So thousands and thousands of calculations are done to explain or to understand how a catalyst material is doing the job at the nanoscale. Now this is still not three-dimensional, I must tell you. Nature is doing probably much better job for thousands of years with these cavities. This material is still not developing those catalysis cavities. Nature is probably much more advanced. As you see, nature is awesome. And mimicking nature is the challenge for this century if you want to provide the sustainable solution on this planet for all the energy need, for the climate change, and fix the problem forever for the next generations, because you have to live and leave this planet and in a much better way so that the next generations coming up should thank you for making something which you are sustaining the whole planet. And that is what you have to see. You have to go out, take your cup of tea, grab it, go out, sit in the nature, sit under a plant, sit under a tree, just like Newton was sitting and the apple fell on his head. Same way you might have to think in nature, how nature is doing it, what is the engineering principle, what is the design principle in these materials. Can I create something like that in my lab? And once you have a lab, do it. Do it for the sake of others who are going to inherit your legacy and your planet. That will be your long-lasting legacy, like Haber sent it to all the planet, that he can fix the nitrogen and provide food. You can probably fix the water, provide energy in a most sustainable fashion, just like the nature is doing. Thank you very much for listening to my talk. I open up for questions. Thank you. Thank you, Professor Rajan. Any questions? No questions? Anyone? Okay, Professor Rajan, I am done. Thank you. Rajan, are you listening?
Yes. Thank you, Ali.
Yeah, thank you.
So I have a couple of minutes for discussion. Asta, yes.
Astha has a question.
Sir, is there any other possibility for types of catalysts other than the ones that have pores? Like we saw that animation and there were porous catalysts and atoms were getting stuck in the pores and then they were reacting. So is there any other possibility for catalysts?
Yes, so there are, as I said, there are different types of catalysts for different types of jobs. There's one thing is photocatalyst, then I said electrocatalyst, there are regular catalysts. Then you are also working biological catalysts, which are known as enzymes. So there are 4 classes of materials. Within the catalyst, like if you talk about just the normal heterogeneous catalyst, then you have homogeneous catalyst, which some actually mix with the reaction. You can't see the catalyst. Some are separate phase. That's called heterogeneous catalyst. Within the heterogeneous catalyst, some could be porous, some could not be. This was not actually porous. This was the surface. This was very big particle, like a metal catalyst. But some are zeolites, which have porous structure. So you have to create, and there are more materials showing up even today, like MOFs or other metal organic frameworks and many other types of materials which are coming on the horizon. So there are new materials are coming every day. So I think when I joined 2000, I did my BTech from 2002 to 2006. And I went to University of Virginia, start my PhD. At that time, catalysis was not that famous branch in science. It's still one of the most, I would say, one of the most contributing, 1 upon 60, like out of all 60 papers published in science today, 1 is from catalysis at that time as an estimate. But now things have changed rapidly. Now there are so many new journals talking about catalysis or catalyst materials because all of these problems are linked from catalysis. Whether you are solving the solar energy, whether you are talking nuclear energy, whether you are talking about batteries, whether you're talking about fuel cells, whether you're talking about photo catalyst to reduce water, all of this. So different range of materials are coming up. And people are exploring the catalytic properties a lot so that you can do reactions in a faster manner. Okay, so some have pores, some do not have pores, depending upon the requirements. Okay, like electrodes in the solid oxide fuel cells have pores, while the electrolyte doesn't have pores. Okay, so depending upon the requirement, you design materials where you keep pores or you don't keep pores. It's all possible. The idea is that one day you are able to reach something like what nature has in design, like enzymes, which is still very, very far away, at least 50 years of road ahead in engineering, because we have not seen still, we have seen some engineering skills at the nanoscale where you can design a material, make it stable. Now people are also talking about single atom catalysts in the last 3 years. Single atom. You don't need 400 atom nanoparticles or 300 atoms. You just play with single atom. And you can change the property of single atom of iron may behave something different. And can you control that property to get a reaction done, and you can make it very stable fashion. And this is a new branch in catalysis these days. In last 3 years, it's called single atom catalysis. Our group is doing many things. Like I didn't show what we are doing, but we didn't get time. But we are doing now. We are also doing with supercomputers how you can create different environments, different solvents. We don't have time, but I will show you one of the things. The last picture. It's very, very artificial intelligence and machine learning. So I wanted to show that. Maybe we get there. Yeah, this is the one. So now from the periodic properties of the elements, we are designing new catalyst materials or single atoms of catalyst. Like this catalyst material is just single atom in the host of a large matrix. And how you make it stable. And we are using machine learning elements or artificial intelligence to design these particles. Okay, and that can do a reaction of your target with high convergence or high selectivity to your product. So no other product, just the product you want. Okay, so these are some of the new ideas which is coming. Of course, you can make it porous, you can make it non-porous, but more than that, how you pick up the right elements which can do the job, and you get the right kind of sites, less like the 2-dimensional cavities or the enzymes having a 3-dimensional cavity. you can make those cavities. So these are the ideas which people are working on. So thank you, Asta, for asking that.
Thank you, sir.
Thank you. Anybody else? Anyone else? So, Mr. Rajan, I think we are done.
Yeah.
There's no more questions. Thank you.
Yeah, I think if there are no more questions, thank you, Ali. Thank you so much for really interesting talk. I think out of the talks we had in last days, it was one of the most interactive talk. So thank you so much. And all the students will meet again at 4 p.m. Thank you, Ali.